السلام عليكم، صباح الخير.
صباح النور بروف. عليكم السلام ورحمة الله، يا أهلا بك.
كيف الصحة؟ أخباركم بخير؟
الله يخليك ويسلمك.
شكرا شكرا.
دكتور احنا راح نبدأ بالساعة 10 إن شاء الله.
أوكي، in 8 minutes تقريبا، صح؟
إن شاء الله إن شاء الله، والبث لايف على الفيسبوك، وأيضا راح تتسجل المحاضرة.
إن شاء الله، شكرا.
إن شاء الله.
بالنسبة للوقت ربع ساعة لكل متحدث، صح؟
هو المفروض ربع ساعة لكل متحدث، بس أحيانا مثلا في متحدث غايب أو متحدث يخلص بسرعة أو متحدث ياخذ وقت أكثر، يعني إحنا نحاول إنه عند نهاية الربع ساعة ننبههم إنه تايم أوت.
وموضوع آخر بالنسبة للأسئلة، هل يعني بعد كل presentation we'll have the question ولا نخلي الكويشنز لآخر السيشن؟
usually حسب المودريتورز، يعني السياسه اللي هم يتبعوها، بس usually انا شفت البارحه مثلا غالبيتهم بيخلوا الدسكشن في نهايه السيشن على كل، مثلا اذا الناس عندهم في question and Q&A they can post their questions over there, then the moderators can read the questions, answer them, some maybe panelists answer them typing or yeah أو بالصوت يعني.
واضح، شكرا. Shall we start or we are going to wait? Yes, I can start whenever you give me the green light, but also I need to get the right to share my screen because for the moment I can't.
Yes, Doctor, you just go ahead and I'm afraid that the other
That's fine.
are not there, but maybe they show up during.
Yeah.
Yeah.
No, that's fine because it's still early morning. But when I share my screen, it's displayed here, host disabled participant screen sharing. So if you could give me the right to share my screen.
Yes,
that would be great.
yes, please.
Thank you.
Yep. You may do it now.
I will check.
Mm-hmm.
Yes, perfect. Thank you so much. Then I will. Do you see my screen right now?
Yes.
Perfect.
Yes, it's there. Yep.
So if you allow me to start, so assalamu alaikum wa rahmatullahi wa barakatuh. Good morning. Sabah al khair, Slav. Thank you so much to the organizers for having me. Thanks in particular to Dr. Amal Amin, Dr. Suhad, and all the team from University of The Hook. It's a pity we couldn't make it to The Hook and Iraq, but hopefully next time we will be in place. So my presentation will be around desalination, sustainable desalination in the Arab region. So the outline of my presentation will be as follows. So I will talk about water scarcity in the region, then the desalination technologies, renewable desalination that could be also used for agriculture, the environmental impact and brine management, the economics of desalination, some future perspective, and finally we'll end up by some conclusions and recommendations. So I think I have in principle 15 minutes. I will try to make it. I have more slides, but I will try to make it inshallah in their own time. So if you look at this map of the water risk in the world, we see clearly that almost 2/3 of the world face water scarcity. And in particular, we have extreme and high risk in the Arab region, as you can see in the red color and the whole Arab region. Obviously, when we talk about water scarcity, we talk about an imbalance between water supply and water demand. So in general, whenever we have water scarcity, the typical question that we ask are, is there water available? Is it accessible? So can we bring this water to our field? The cost is another question. So can we afford paying for that water? Probably we have water, but it needs a cost probably to treat it or to bring it to my field. And the other question is the quality. So is the quality which is available is responding to my needs for drinking or for irrigation or whatever other purposes. So in general, the actions that we think about, when we talk about water scarcity, so the typical response is to increase the supply. So how to increase the supply? So if we don't have enough conventional water resources, so we can look for non-conventional water resources, which are basically desalination, which is an option, but also we can also treat wastewater and reuse it. So this is one way to increase the supply. Also, we can think about conserving and preserving the quality of the water that we have. We can also try to increase the water use efficiency and productivity. We know that in the Arab region, almost 80% of the water resources are used in irrigation, and the efficiency is almost not higher than 30%. So a lot of water is lost in irrigation and in agriculture. So the way is to increase the water use efficiency and the water productivity, which means that we produce more with less drops of water. I cannot move this. And also we can think about reviewing or revising the water demand, because in general, we think about supply, but we forget about demand, because some of the highest water consumption per capita in the world are, for example, in some of the Arab countries, especially in GCC, because the water sector is subsidized, is cheap. So people don't think about conserving the water. So they consume more than what we can afford really. So those are some of the reflections about water scarcity. So I will focus on one of the options, which is desalination. So as you know, ocean makes almost 70% of the Earth's surface. That accounts, it accounts for around 96 to 97% of the water on the planet. So desalination is basically the process, is the large-scale effort to remove salt or fresh water from seawater. And today we have almost 20,000 desalination plants around the world, producing almost 100 million cubic meters per day of fresh water. And so it is again this technical process to get fresh water from the salty water. But we can distinguish between different kind of desalination technologies according to the energy source that we use. So whether it is mechanical, thermal, or electrical energy to separate the water from the salt and produce fresh water from one side. And we produce, unfortunately, also a concentrate which we need to deal with. So typically, so this is not all the desalination technology, but some of them. So we have what we call heat-driven processes like MSF, MAD, membrane distillation, humidification, dehumidifications. And we have what we call power-driven processes like reverse osmosis, RO, electrodialysis, or forward osmosis. And we have power, between like mechanical vapor compression between both processes. If we look at the international market right now, almost 70% of diesel plants are based on RO, or reverse osmosis. Then we have in the second place MSF, multi-stage flush, around 18%, so which is thermal desalination, which was more popular in the past, but because of some reason that we will explain in the next slide, the scenario changed, and we have now more and more RO plants than thermal desalination plants. The RO system, or the reverse osmosis desalination, typically we have three phases. We need to do pre-treatment of the water, the feed water, and then we use a high pressure pump to push this water to the RO modules or the RO membranes, and we use energy recovery devices to optimize the use of energy and improve the energy efficiency. And we produce from one side, as I said before, fresh water. From the other side, we have the brine discharge. So we have the RO phase, and then the post-treatment, according to the use, whether we are looking for drinking water or we are looking for irrigation, whatever. So we can adjust the post-treatment according to this final use. So as any other technology, RO has some advantages and some constraints or limitations. When we talk about advantages, I can mention here, it is suitable for desalinating both seawater and also brackish water or saline groundwater. It requires less energy than MSF, MAD, VC technologies. So almost it's much more efficient in terms of energy than thermal desalination technologies. Also, it requires lower investments and total water cost than other technologies. In terms of limitations, the quality that we are producing using RO, it's between 250, 500 milligram per liter salinity, which is still obviously suitable for drinking purposes. The membrane replacements, so sometimes or often we need to replace membrane after a certain time because of some factors, I will mention them. We need to replace the membrane, so this add to the cost. High operating pressure, electric energy, so still we need a lot of electrical energy. We need also continuous membrane cleaning, so because of the fouling, scaling, etc., that happen to the membrane, depending again on the feed water quality. So we need to do the chemical cleaning of the membrane. We have also limited recovery rate, which means that we are producing also a lot of brine. The brine is this concentrate salty water with eventually also some chemicals that we need to find a way to manage, instead of re-injecting it in the aquifer, or we could contaminate the groundwater, etc. Or maybe in the seawater, we may also have harm the marine ecosystem. Then also essential extensive pre-treatment and post-treatment, which is also required. So we need a lot of chemicals during the pre-treatment, but also at the post-treatment. Then significant capital investments and has relatively high operational cost. And the brine disposal, as I mentioned, which is the main environmental impact concern that everybody is questioning. If we look at the world, we have, as I said before, around 220,000 desalination plants producing around 100 million cubic meters per day of desalinated water, and we are consuming every day around 200.
شكرا. بعدين من معكنا هنا هم بديش يتم سماعات محكوة نبقى.
If you could please mute your mic.
بس من داخل chat. شكرا.
And we are consuming around 250 million kilowatt hour per day in those desalination plants. If I can ask the organizer to mute, I mean, everybody, because otherwise we will not. Thank you. So in terms of the cost, if we compare the cost of desalination now with the 80s of last century, there is no way. I mean, the cost has decreased considerably because of a lot of improvements in terms of more efficient pumps, better membranes, better energy recovery devices. And we are talking now about a record in one of the UAE desalination plants, Hassian. We're talking about $0.3 per cubic meter, which is really, really very low. Compared with in the past, we were talking about dollars per cubic meter. So we really did a big improvement in terms of the cost of the desalination technology. If we look at the Arab world, so the biggest desalination actor is Saudi Arabia. They are producing around 15 million cubic meters per day, followed by UAE around 10 million cubic meters per day. And there are still many projects on the pipeline. For example, Saudi Arabia, they are planning in the next upcoming few years around 9 big desal plants on the shores of the Red Sea. And we have many other projects also coming in Morocco, in Tunisia, in Egypt, in Algeria. So the region is producing almost half of the produced desalinated water worldwide. So this is obviously huge. So then the question is desalination the solution to ensure water security? Because as I said before, in the last years we are suffering. We have water scarcity exacerbated by climate change. We have more pressure on water resources from the economic sector, and we have the growth of the population. All of those factors make more pressure on the water resources. So desalination is becoming more and more present in all the water strategies and the water planning in all the Arab region. So we can find it in the Arab water strategy, in the strategy, everywhere in the national water strategies. But obviously, this solution, as I said before, is still costly, energy intensive, and also we have this environmental degradation, which is a major concern. Apart from the desalination technologies right now are still relying on fossil fuels, so we have this concern of CO2 footprint and the Paris Agreement. How can we commit to Paris Agreement if we continue relying on fossil fuels in this field? So there is a need to develop less polluting and more energy efficient desalination technologies. And also in terms of even in the touristic sector, for example, which also requires a lot of water, we can also be a rich source of income for improving water supply and sanitation system for local populations. So in many now touristic complexes in some countries, they are using desalination to provide water to the touristic complex. So if we consider desalination as a sustainable solution, this necessarily pass by responding or giving solutions to those four elements. First, the energy consumption. So we need to reduce the energy consumption. So why RO is now dominating the market is simply because now it is more energy efficient than thermal desalination technologies. In terms of cost, also capital costs and operational costs, we need to reduce it. In terms of membranes, fouling, sculling that happen often to the RO, especially technologies. So we need also to find better membranes and to find solutions for the sculling and fouling and biofouling. And in terms of environmental impact, so the energy consumption, again, the carbon footprint and the rejection of the brine or the brine disposal, we need to find solutions. And we have two kinds of impact. When we talk about big desal plants in the sea, the sea desalination, seawater desalination, we talk about impact due to the intake, when we install the intake, wherever we install the intake system, it may have a bigger or smaller impact on the marine ecosystem, and also the impact due to the discharge. So discharge also has an impact. In terms of energy demand for desalination, so we had done a very big improvement in the last years. The average for RO was around 3.5 kilowatt hour per cubic meter. But if you can see here in this figure, in the last years, we even reached 2.1 or 2.2 kilowatt hour per cubic meter, which is very, very low. And we are really going closer to the thermodynamic limit, which is around 1.3 kilowatt hour per cubic meter. In terms of renewable desalination, so this is the way actually at small scale is now popular and successful. So the challenges that we have in renewable desalination, which means that we power our desalination plants with renewable energies, that renewable energy generation needs adjustment for continuous supply. And desalination technology can adapt to variable operation, hopefully. So in general, the desalination technology work in steady state conditions. But renewable sources are usually no stationary. So whether we talk about solar or other kind of renewable energies, so they are not stationary. So we need to find this adjustment to make it work. So solar desalination, as I said, is becoming really popular. So we have so many plants in the Arab region and worldwide that are relying on PV photovoltaic that are producing electric energy to run the desalination system. And we have also other plants using windmill or even eventually we have other combinations between solar and MSF, solar MED, not all the time with RO. And a lot of studies by the scientific community, they showed, that PV-RO probably is the best for the moment as the best combination, followed by probably the wind RO. And obviously, the advantage is that we reduce RO plants' carbon footprints, we decrease the running cost, we eliminate the link between water prices and the fuel cost. And obviously for remote areas also, it's a perfect solution. Whenever we don't have electrical grid, this solar desalination could work really well. But obviously we need to choose also between two configurations, whether we need to rely on batteries, because obviously we can run the solar desalination plants during the day, and in the night maybe we need batteries, or maybe we need other configuration, which is to connect it to the electrical grid, which is sort of hybrid system. Or maybe we can just have a standalone configuration, and we produce enough water that we can use also during the night. So in the region, we have so many plants, as I said before. So we have some examples from Qatar, Algeria, Tunisia. In Saudi Arabia is the biggest plant right now powered by solar, which is Al Khafji plant, producing 60,000 cubic meters per day. So as I said before, the benefit of solar desalination include it use free solar energy for operation. They are inexpensive, light in weight, and easy to transport. We can transport them from place to another. The plants can be set up easily, either onshore or offshore. We have low maintenance cost, and it is environment friendly, obviously. This is just an example of Elemental Water Makers company, which is producing solar desalination units, and which are very popular in some islands. We know that some islands, for example, in the Mediterranean, like Malta, Cyprus, even the Maldives, all those islands are relying almost 100% on desalination desalinated water. So these solar desalination solutions are really perfect because we are making a big saving. Those are other examples from Morocco and Tunisia here. So those are systems deployed by a Spanish company, and it's a PV-RO, and they are producing enough water for some villages, some users. So some parameters here, I will not get into details, but this kind of project are really successful. If we compare, so the plants of 500 to 5,000 cubic meters per day, we compare between PV or solar thermal powered plants with the conventional plants, we see that we are going closer to the conventional ones. So we are becoming really competitive in terms of renewable desalination in the market. Also, desalination could be used for agriculture. Spain, for example, a lot of farmers in Murcia, Almeria, they are using desalination for agriculture. Here, I show you one desalination units in my center in Oman, when I've been working the last 5 years. It is powered by PV and producing 1.3 cubic meters per hour. of fresh water. It was meant to use for to be used for irrigation. But we need to take into consideration some aspects. One of them is that we need to use it for high value crops. We cannot afford to use it for low value crops because it will not be economically feasible. And also we need to do some arrangement also for the brine, how we can deal with the brine, and also for the desalinated water itself. Because of the quality of the produced water, we need probably to mix this desalinated water with less low quality groundwater for the benefits of the crops, depending on the crops. But I think we can learn a lot from the experience in Spain, but also we are using desalination for agriculture in Oman, in the UAE, in many other countries in the region. This is just some photos from one of the farms. We have this RO system. We have the evaporation pond, which is one of the solutions to deal with the brine. So we pump the brine to this pond, and we wait that this liquid evaporates, and then the concentrated salt, we can deal with it. In terms of environmental impacts, I will try to hurry up because I'm over time. So we have the seawater intake, the land use and construction impact, because we are talking about big desal plants almost on the shores. We have the concentrated chemicals, which we find in the brine, and we have the CO2 footprint or the air pollutant. So the brine disposal is an issue for all the technologies. With the thermal or RO, we are producing this concentrated liquid with eventually toxic brine we can have, and so we need to find solutions instead of disposing it as it is in the sea or in inland. This is the typical outfall with diffuser designed to reduce salinity down to 10% of ambient levels within 100 meters of the discharge. We can find this in all big desal plants. So we dispose this brine into the sea. We have some standard we need to follow, and we have also the regulation. The regulation should be strict enough to reduce this environmental impact. In terms of impact due to the discharge, so as you know, when we discharge the brine, we are discharging it, for example, in the seawater desalination, we are discharging in the sea, and we can have salinity increase, we can have temperature increase, in particular for thermal desalination. We can have decrease in dissolved oxygen, and have an increase in toxicity, like chlorine, trace metal, and other chemicals that we use during the pre-treatment or the post-treatment. So in terms of brine, so the high salinity could affect, the marine ecosystem and the temperature as well. It's because of the thermal shock, some fishes we know cannot survive, and sometimes we have the increased proliferation of the harmful algae blooms. This is a very big problem in the coast of in the Gulf, because whenever we have this high concentration of algae, the desal plants sometimes stop production, or they have a lot of problems in the pre-treatment, because those algae, when they pass to the plants, they cause biofouling, and we need to increase the chemical cleaning. And eventually, in the last years, we invented the DAF system, which is dissolved air flotation. It seems that it's a quite efficient pre-treatment system to deal with the algae blooms, but still is a problem. And the chemicals, obviously, I won't go into details, the different kind of chemical that we use during the process, so that could be really harmful. Whenever we have a desalination project, we need to do the environmental impact assessments. And one of the elements that we use, we need to consider in this environmental impact assessment study is the place where we should construct or build our desal plant. We need to build it in a place where we can have the less or the minimal environmental impact. So we need to avoid, the places where we have the fish eggs and the phytoplanktons, the plankton areas which are very, rich in terms of biodiversity. So to avoid impacting their ecosystem. There are other considerations that we need to take into consideration. For example, in some plants, we have what we call beach well intake system. And this kind of beach well intake system, we cannot do it everywhere. It depends on the geology of the place. In Oman, for example, we have only one plant in Sur, which is using beach well intake system, which means that we bring the water from a beach well, which is connected to the sea. This way, the quality of the feed water is very good. We don't have a lot of problems. And when I asked them last year, they didn't change the membrane almost the last I think 8 years. So they never changed the membrane. So this is that show the advantage of the beach well intake, but unfortunately we cannot do it everywhere. Some precautions, as I said, so we need to stick to the regulation. We need to do the dilution of this brine, you know, in the sea, and we know we sometimes even we need to pre-treat this brine before disposing it into the sea. In Barcelona, for example, the brine produced by desal plants is diluted in the pure treated water of the nearby wastewater treatment plant, so before discharge into the sea. So these are some of the ways to deal with it. Another problem that could happen in the future, especially, is the solid waste disposal, because with more and more desalination plants in the world, we are going to use more and more membranes. And the membrane, after a couple of years, we need to dispose them. So in the center I've been working in the last years, I proposed to recycle those membrane and use them for other kind of wastewater treatment applications. So when we get rid of the last layer of the membrane, we can still use them or convert them into nanofiltration or microfiltration membrane that could be used to other wastewater treatment processes. The carbon footprint, so RO, we are talking about 1.5 to 3.6 kilogram CO2 cubic meter. And thermal, it's more like 8 to 16 in med or MSF, it is 10 to 20 kilogram CO2 per cubic meter. But is in the worldwide, is around, we are talking about less than 0.2% of worldwide energy consumption. And so somehow the CO2 footprint is less than other industries. The economics, so the cost of cubic meter is very complex issue. We need to compare a lot of parameters. So it depends on the feed water, depend on the technology, depend on the quality required, it depends on many factors. So this is just a rough comparison between the seawater cubic meter cost in the Mediterranean and MSF, MAD, seawater RO. So we have between 0.5 to $1.5 per cubic meter. And if we need to calculate the cost of cubic meter, for example, in RO, we need to take into consideration all what you see in this slide. So we need to see the intake system, which kind of intake, the capacity, the pretreatment, also which kind of filters we are using, the RO system, which kind of membrane, how they are, the configuration of those membrane, energy saving, which kind of high pressure pump we are using, the post-treatment, so all those parameters. So it's quite complex issue. In the perspective, I mean, Nikolai Voichkov already expected that we are going to go to $0.3 per cubic meter. Or we already reached it in UAE, it seems. So we definitely are doing a lot of improvement in terms of the cost. In terms of technology by CAPEX, so we see that the expectation that the membrane-based technology like RO are going still to dominate the market in the upcoming years instead of the thermal. Some top 10 technology disappointment. I just try to show you this slide to show you that sometimes we get excited by new technologies in some publications that we see in the journals, and after some years we realized that it wasn't really realistic, because there is a difference between what we do in the laboratory and what is the real condition in the market. So between developing the technology in the laboratory, to upscale it to the market and make it competitive, it's really difficult. So it takes years, it takes a lot of improvements. For example, 2 years ago, a researcher from the Manchester University published a paper in Nature talking about the graphene membranes that could be really potential for the future desalination plant. But since then, nothing happened yet, because it takes really time to have it in the market and prove that it is working and better than other technologies. So the best hope, hopefully in the next years, is that we are going to get better membrane, hopefully maybe a new approach to desalination, maybe better energy recovery devices, maybe we have some hybrid processes that could improve the process, and other areas. This is just to show you some areas where we can still improve the technology. Conclusion, so adaptation measure to reduce water scarcity in the Arab region. But again, we need to shift to renewable desalination in the future. We have less, we have more and more renewable desalination, especially at low scale. But at big scale, we are starting working on that. So we have, I said, the plant of Al Khafji in Saudi Arabia. There is Perth plant in Australia, 120,000 cubic meters per day, which is fully powered by windmill. So we are starting, you know, shifting to the renewable desalination. So we need to follow the trend. Seawater desalination is vital for Arab countries, and the reliance on the source is expected to grow fast. The growth will only be possible by continuing to improve, you know, sustainability of those technologies. Solar desalination is a good example of water energy food nexus implementation. So we have a lot of greenhouses in UAE, in Oman, in Spain that are, you know, using desalination and using solar to produce crops. And this is very, very, very interesting solutions. So that's why we are dealing with not only SDG 2 and 6 and also 7. For desalination to become really an alternative to alleviate water scarcity and the climate change adaptation option in our region, all stakeholders need to be consulted extensively. So, for example, now it's becoming popular to adopt the PPP approach, which means that the public-private partnership approach, which means that big desalination project, the government and authorities cannot afford to pay for it. So we need the private sector. So in a good deal between private and public entities, we can develop desalination project in a win-win deal and in formulas like BOT, build, operate, transfer. So during 25 years, for example, you build and you operate, and then you transfer back the plant to the government, for example, in the case of some project, like, for example, Agadir plant in Morocco. So by design incentive for local business and government can attract domestic investments. So we need also to invest in R&D and in localization of the technology, because during 50 years now, we are using desalination in almost all Arab region, and still we are importing all the component desalination plants. During the first month of the pandemic, for example, when China closed the borders, we were really worried because we cannot have chemicals, we cannot have some component that we need in our desalination plant. So we need to develop this kind of localization in our region. I think there are some efforts in Egypt, in Saudi Arabia. Hopefully this will go further. Last slide, the recommendations. So as I said, PPP, BOT, for example, and other innovative financial mechanisms to support sustainability of desalination schemes will likely be required. The MENA region needs to localize the knowledge, not also the technology also, but also the people. We need to train people to develop more capacity building in this area. And finally, probably this is just my recommendation to you to have a sort of observatory at regional level where we can really give an advice, we can help, and we can orient policies and advise, decision makers in the region. 2 years ago, I organized the conference with the Islamic Development Bank in Oman. I invited 10 Islamic countries, and we talked about the technology of desalination. We talked about the challenges, the solutions, and I think this kind of gathering and this kind of effort should be encouraged. Thank you very much. I'm sorry for taking more time than what was expected at the beginning. If you have any question, probably as I was discussing at the beginning with the organizer, maybe we can shift, please note your question, the Q&A, and then we will respond to all the questions at the end of the session, okay? So we have still for presentation. Thank you very much for your attention. This is just to show you one study I published early this year. If you want to get more information about this technology in the region, so feel free to download it through this link, or you can contact me. I can send it to you. Thank you very much again. So I think according to the plan, we have now the second speaker. I will stop sharing. So yes, so the next speaker we have with us Dr. Shayma Hamid from Egypt, from the National Research Center. She's going to talk about greywater treatment for irrigation purposes using pottery scraps and aerated moving bed biofilm reactor. So if I don't know if the organizer allow me, so the floor is yours, Dr. Shayma.
اوكي صوتي واصل كده كويس؟
ممتاز، perfect.
اوكي خلاص. اوكي هعمل شير سكرين. Okay, I will start. Assalamu alaikum. Hello everybody. I am Dr. Shayma Ragab Hamid from National Research Center of Egypt. It is my pleasure to be here with all of you. I will present my lecture under the title Greywater Treatment for Irrigation Purposes Using Pottery Scraps and Aerated Moving Bed Biofilm Reactor.
Dr. Shaima, if you could put it in full display, maybe it's be
Okay,
better. Thank you.
I will do. I will do.
Thank
Okay.
you.
Okay. We will speak about grey water. What's meaning of grey water? I mean in grey water, the water were collected from kitchen, laundry, bath water. Grey water contains suspended solids, organic surfactants, but have a low concentration of other organic matters, nutrients, and also pathogen. ده بالمقارنة بالبلاك ووتر. كان بيتم عملية كولكشن تجميع لكل من الجري ووتر والبلاك ووتر، ويتم عملية ديسشارج ليهم في نظام الصرف الصحي المختلف. ولكن نتيجة الجلوبال شورتج اوف فريش ووتر ريسورسز، بدأ العلماء يفكروا ازاي اعمل تريتمنت عشان اقدر استخدم ريوز اوف جري ووتر بالنسبة للإريجيشن. فكان وده اللي ده له مميزات كتيره جدا. اول حاجه بعمل ريدكشن اوف فريش ووتر and ريدكشن بالتاكيد للكوست فور تريتمنت and the supply of drinking water and reduction in collected quantity of black water which reduce the cost of treatment and of course and the sewage treatment. Treated groundwater can be reused for specific purposes such as garden irrigation, toilet flushing and car washing. طيب ازاي اعمل معالجه للجري ووتر؟ كان في different methods, physical, chemical, biological, but there is no technology when applied singly become effective. بمعنى ان انا محتاجه ان انا استخدم more technology اكتر من تكنولوجي عشان اقدر اوصل للنتيجه اللي انا عايزاها. النرويج في طريقه كان تم استخدامها اللي هي MPPR اللي هي Moving Bed Biofilm Reactor، والطريقه دي بتعتمد على الability of different microorganisms to form biofilm، وعن طريق البايوفيلم ده بيتم عمليه degradation للاورجانيكس ماتر، تقليل البي او دي والسي او دي زي ما هنشوف. فاحنا فكرنا ان احنا نستخدم طريقه MPPR بكومباينيشن with pottery scarps اللي هو الفخار. الفخار طول عمره بيستخدم في مصر من قيمه 7000 سنه كافضل طريقه للووتر بيوريفيكيشن، وما زال بيستخدم حتى هذه اللحظه في كتير جدا من الايجيبشن فاليج واستخداماته كويسه جدا. فاحنا فكرنا ان احنا نستخدم البوتشري سكاربز في مع MPPR ان احنا نعمل عمليه تريتمنت للجري ووتر، وطبعا عملنا طبعا سبلمنتد وذ هيدروجين بيروكسيد از ديسانفكتنت. اوكي. طب هنشوف عندي بعد كده الماتيريال اند ميثود ازاي احنا عملنا الشغل ده. اول حاجه هو الناتشرال جري ووتر. جمعنا جري ووتر فروم 3 هاوسز، من 3 منازل لاشخاص طبيعيين في احد القرى المصريه. المنزل الاولاني كان بيحتوي عندي على 3 بيرسونز، والثاني 4 بيرسونز، والثالث 6 بيرسونز. وكنا بنجمع يوميا حوالي طبعا احنا كنا بناخد الميه بتاعت الكيتشن واللاندري والباث، مالناش دعوه بالبلاك ووتر، وكنا بنجمع في حدود حوالي 120 لتر من الجري ووتر، وبيتم تجميعهم في 200 لتر بلاستيك كونتينر. وطبعا بعد كده بناخد عندي الجري ووتر ده بنعمله كاركترايزيشن اللي هو الفيزيكال والكيميكال والبيولوجيكال بارامتر زي البي او دي والسي او دي والتي اس اس والبي اتش والتربيديتي والتوتال كيليوفورم اند الايكولاي. وبعد كده بدانا نصمم اللي هو البي اس سي كولمان يونت اللي هو البوتري سكاربس كولمان يونت، وده اخذنا سكاربس من احد المصانع وبدانا نكسرها مانيوال، وكنا يعني متعمدين ان احنا نكسرها لثلاث احجام مختلفه، large, medium, small، وبدانا نحطها placed in polyethylene plastic كولمان كان الدايمتر بتاعته 40 سنتيمتر in diameter and 1 meter in length from the bottom to top according to scarp size. طبعا كان في البوتوم هو الاصغر ثم الاكبر ثم الاكبر and التوب. وكانت الخطوه اللي بعد كده عملنا ستانلس ستيل نت. كان عملنا نوعين، النوع الاولاني كان البور بتاعته 20 ملم، ودي كنا بنستخدمها نعمل سيبريشن بين ذا توب اند ذا ميديوم، والنت الثانيه كانت البور بتاعتها 3 ملم، ودي كنا بنحطها اندر ذا بوتوم لان بالتاكيد في البوتوم كان موجود عندي الاحجام الاصغر من الباتري سكارف. واستخدمنا مجموعتين من البي اس سي. ليه؟ علشان احنا كنا بنعمل عمليه تغيير للبي اس سي اللي هو البوتري سكاربس every 2 days. بمعنى ان انا كنت
دكتورة شيماء, sorry for interrupting you. I was asked by the organizers if you could please shift to English. I will be grateful. Maybe some people are preferred it in English, so if you could please make it in English.
يعني كله اوكي مفيش مشكله.
Thank you so much. شكرا. Thank you.
ماشي اوكي. After that, 2 sets of PSC layers were used alternately every 48 hours, and another steps in MPPR setup. Capacity of MPR is about 200 liters. Inside it, both cylindrical polyethylene plastic biomass, and the MPPR was operated 2 weeks before the experiment to allow the formation of biofilm. The required oxygen for aeration was supplemented into the MPPR tank using an aerator. So finally, the storage and disinfection tank. The storage tank capacity will be its capacity 200 liters and disinfectant by hydrogen peroxide. This our tank and designed by our partners, Dr. Mohammed Nabil in Brine Disposal University and Dr. Ra'ad Al-Wasifi in National Research Center. As we see, that's the first tank. It is the collecting tank. We collect the raw grey water, and the second tank in the PSC unit have 3 layers of PSC, as we see, large, medium, and fine. And finally, the MPR tank, which have the cylindrical plastic biomass carrier, and the collecting tank, which have the storage tank and make the hydrogen peroxide as the disinfectant used in the final storage. Okay, we collect 4 samples every 6 hours after PSCU, and also at the end of the daily operation, 1 sample was collected after MPPR. The daily results were recorded, and the average of all collected after 30 days system operation. The second cycle will begin after emptying, of course, the collection tank from the second cycle. Results and discussion. We see in the first table, characteristic of right grey water. A pH from neutral to slightly alkaline from 7.1 to 7.9. In natural pH, it's maybe due to the grey water come from the kitchen or tap, and the alkaline comes from maybe the washing water due to soups and another. Turbidity about 58 points, and that due to grey water have a high concentration of suspended matter. So as this appear in TSS, it's high. It's about more than 484. And the same thing in grey water have a high concentration of the COD and the BOD. Average counts of both total coliform and E. coli in grey water were less than those reported by another studies in Egypt. I talk about Egypt, and this may be due to family makeup. We noticed that the family would have more children than adults. Total coliform and E. coli would be high. Other families would have adults more than children. We have less concentration in total coliform and E. coli. Then, okay, treatment of performance PSCU at the CU in the table number 2, it was clear that there is no considerable effect of PSCU on removal of organic matter in grey water. The removal efficiency where it's so low in POD and the COD, as we see, it's less than 10% in the both in POD and COD. But in the contrast, the removal effect of PSCU was clear in turbidity, in TSS, in total coliform, and E. coli. And I think that's maybe come from the nature of PSC, the nature of course, the compounds of PSC. It maybe have many reasons. Treatment of performance of MPR. There is many factors which affect the performance of MPR, maybe biofilm formation, type, characteristic of biofilm carriers, aeration, meaning. The removal efficiency of POD and the COD after MEPR, it's high. It's more than 95%. Because of, I think, the most of organic matter in groundwater will degrade it. So it's affect, of course, it affects in POD and COD. Turbidity, of course, it's high also. It's removal high. It's more than 93, and TSS 97%. Hydrogen peroxide, it's come from the end of the pre-treatment operations, has a strong effect in self-destruction power. So it's kill about 99% of all my bacterial contaminations. But all these results, we can use this treated water in irrigation purpose according to Egyptian guidelines. In Table 3, summarized the average value from treated groundwater from Table 2 in comparison with the Egyptian guidelines for wastewater use irrigation, so and restricted or unrestricted. We found that it is clear that our treatment system produced effluent, particularly to TFS, COD, E. coli, which satisfy the Egyptian guidelines for both restricted and unrestricted irrigation. Our conclusion from the obtained results in this study, it can be concluded as the following. PSCC could be used as a neutral filter medium in groundwater treatment process because it was shown great and ability in removal turbidity, TSS, and the coliform and E. coli. And I think it is a very important point in irrigations because we don't make contamination for the plant. The using of PSCC as a primary treatment step improved the treatment performance of MEPR by improving the quality of raw grey water. MEPR provided high performance in removal of organic matters in terms of POD and COD present in groundwater. The treated effluent meet the Egyptian guidelines for both restricted and unrestricted irrigations regarding to, as we see before, TSS, COD, and E. coli. And we can use hydrogen peroxide in disinfection. It is more safety than use chlor because you have no lethal effect on the water in the treated water and have good effect, the least effect on the microorganism only by make the generation and for genome of bacteria. At the end of my presentation, I will thank my partners, Dr. Adel Wasifi and Dr. Mohammed Nabil, and thank you.
Thank you very much, Dr. Shaima, for this insightful presentation and also being on time. You managed the time better than me. Thank you very much. So I think we need to pass now to the third speaker, Dr. Sarwar Mohammed Rashid from Iraq, from the University of Duhok. He will talk about effects of leaching with magnetized water on 3 saline soils. So Dr. Sarwar, the floor is yours. Thank you.
Yeah, Assalamu alaikum. First of all, I'm not a doctor, I have an MSc. Thanks for you for allowing me this opportunity to participate in this online conference. So now I will share my screen. Is it right now? Dr. Jawad? Dr. Jawad, is it right now?
Yes, it's clear. Just go ahead, please.
Oh, okay.
Yeah.
It's now full screen, please.
Sorry?
It's now full screen, the PowerPoint.
Well, if you present Go to
Okay.
the presentation, F5 maybe.
Okay. My research is entitled "The Effect
Please
of."
convert your slides into the presentation. I mean,
Sorry.
you go to the slideshow.
Oh, okay. Okay. I'm making, but I don't know why it's not.
Oh, so you have two screens maybe, so you have to focus on the presentation. You may share the other screen where you present. Yes, yes. Okay, no. Go to the other one. You just
Okay.
made it.
This one?
Yes, yes. Please keep there. Keep there and continue. Yeah.
Okay. My research is entitled "The Effect of Leaching with Magnetized Water on 3 Saline Soils." Introduction. Saline soils increased in central and southern parts of Iraq due to the rise of saline groundwater and the use of poor quality irrigation water. The available water for leaching is limited and contains various dissolved salts in it. Using magnetic treatment, which denoted by MT, thought to be effective in dissolving and leaching salts from the soil. A number of studies on effect of magnetic treatment have been carried out in different locations of the world, but information on the effect of magnetic treatment on leaching of individual ions used during the leaching process is lacking. The present study was carried out to study the role of magnetic treatment in leaching of individual ions from soil having different salinity levels. Our materials and methods, we have columns, we had column experiment was conducted to investigate the efficiency of magnetized water on leaching individual ions from saline soils. The study involved 3 different saline soils ranging between 38.14 to 85.91 deciments per meter leached with magnetized water, which denoted by MW, or non-magnetized water denoted by WW. Treatments in triplicate were arranged and successive effluents or seepage were collected and analyzed. We have a result and discussions. In the first table, we have the pH and EC for an experiment compared components of 3 saline soils and irrigated or irrigated with 2 types of water, as we said before. The pH of the pore volume have little difference among the 3 saline soils, while we have data also shown that have higher amounts of salts were leached in PV1, as you show the blue column. Rate, however, slowed down gradually with increasing the pore volume from 1 to 2 and 3, and then the great amount of salt leached from magnetic treatment, MW. In the table 2, we have a cations leached from soil through a pore volume. No values were measured for the first pore volume because the effluent of the first pore volume was very concentrated, and we diluted to 250 times dilution, and it could not be measured. So we haven't the first pore volume. The Na was leached in higher quantities as compared with with Ca and Mg. Higher amount of Na was leached under the pore volume 1, 2, and 3. But after the PV3, the difference in decrease was small because the maximum amount of Na concentration leached from the first 3 pore volumes. In case of water treatment, values of Na were higher in the leachate of WW treatment, which is the well water for the all pore volumes. This may be indicated that the higher amounts of Na was leached in the PV1, which couldn't be measured, as we mentioned before. And the amount of leached Na was higher from S1 and followed by S2 and S3. And this may be attributed to the higher initial salinity and texture. The Ca, calcium, and magnesium concentrations showed similar trend as Na. After PV2, both concentrations decreased then increased. For anions, the Cl, SO4, and HCO3 showed trend similar to Na, while CO3 carbonate was present in small quantities in leachate. Most of Cl, as you see, was removed from the soil during PV1, indicating that the source of Cl were highly soluble NaCl and CaCl2. Considering the water treatment, generally the total amount of Na, potassium, calcium chloride, and SO4 were less in the leachate of magnetic treatment. And this may be attributed to the magnetic water promote leaching process in the initial stage of the salt leaching, which is the pore volume 1. But as the leaching process progressed, the salt concentration decreased. This can be indicated by the darker color and more concentrated PV1 leachate of the magnetic water treatment compared to well water treatment. Among the soil types, we have 3 soil types have a different salinity. Generally, more cations and anions were leached from the highest initial soil salinity, S1. Its EC is 85.91 decisiemens per meter, followed by S2, 53.92 decisiemens per meter, and the S3, which is the last soil type, 38.14 decisiemens per meter. Table 4 shows the analysis of soluble ions in the soil after leaching, after having the 5 pore volumes. After the 5 pore volumes, concentration of soluble Na decreased sharply to reach a value below 2.74 millimole charge per liter for well water treatment and 3.16 millimole charge per liter for magnetic water treatment. Ca concentration decreased to half, and there was also a noticeable decrease in Mg concentration. Conclusion: it can be concluded that the above results that were leached in the PV1 were higher for magnetic water treatment, but after PV2 there was hardly any difference between treatments. The EC decreased from 85.91, 53.92, and 38.14 14 decisiemens per meter for S1, S2, and S3 respectively, to a range of 2.99 to 3 decisiemens per meter. The PV5 was adequate to decrease the NA values from 718.58, 549.03, and 419.85 millimole charge per liter for S1, S2, and S3 respectively, to less than 50 millimole charge per liter. And at the end, I want to thank my partners, Dr. Khalida Abdul Karim Hassan and Mr. Farhad Ali Hashim, and thanks for you all for this attention.
Thank you very much, Dr. Sarwar, for this very interesting presentation. Thank you very much. So again, to all the participants, please put your question in the Q&A window, and we're going to respond to them all at the end of the session, okay? So right now, we will pass the floor to the following speaker. So we have the pleasure to welcome Dr. Kamil Youssef from the University of Zakho in Iraq. He will talk about the characterization of the airborne particles collected in the Hope city by using various techniques. Dr. Kamil, the floor is yours.
Hello. 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 Hello.
تفضل.
Hello.
Yes, please.
دكتور كامل انت ويانا تفضل.
Okay, thank you. Hi everyone. Sorry. So the name of my title, the title of the presentation is Characterization of Airborne Particle Collected in the Hook using the various techniques.
ممكن بس تعتمد على أن يصير عندنا echo.
Okay.
Yes.
Introduction.
Yes.
Particulated material is one of the major atmospheric pollutants.
Share your screen, please.
Okay. It's okay now?
Not yet.
It's okay?
Right now we see you, but we don't. You have the share screen bottom at the bottom. I don't know if you see it close to the record.
Share.
Exactly.
Yes.
Click on it.
It's okay now?
Not yet.
No. When you share your screen, do you have to select the screen you need to share, and we can see your screen after that. So you have to click share like twice. دكتور بس تضغط على الشير سكرين الخضراء اللي تشوفها راح تطلع لك شاشة.
اوكي اي بريس ضغطتها ما ادري يصير.
تضغط مرة ثانية، يعني لما تطلع لك الويندو تضغط مرة ثانية.
يعني هذه جو فيديو فهم الشير هاي الشير.
عادة لما تضغط على شير سكرين بيطلع لك ويندو ولازم you need to click OK again بعدين بتظهر. Otherwise no issue, Dr. Kamil. You know what? I don't know if you send your presentation to the organizers. You can send the presentation right now, and we can display it on your behalf. No, now it's okay. Now it's working.
So okay now.
But
it's okay.
I see myself. I don't know what is this.
Yes. هسه إذا تختار ال PowerPoint maybe.
Okay. No. You see the PowerPoint.
Exactly.
حتى تطلع على الشاشة.
نعم.
دكتور خلينا نسوي شير سكرين لكل السكرين وليس للسوفت وير محدد حتى احنا نقدر نوصل للباوربوينت اذا صعبه على حضرتك.
ما هسه نشوفها. اوكي.
هو محكي لي اياها كم عنده by using different content.
Okay. Is it okay now?
Not yet, no.
نعم.
لا بعد.
اوكي.
No, not yet, no.
دكتور كامل سوي المينيمايز للزوم مالتك وروح افتح الباوربوينت بالكمبيوتر مالك.
هسه فاتح الباوربوينت.
زين بالشير اختار الباوربوينت تطلع شاشه قدامك بها كذا خيار اختار الباوربوينت. ارجع اسد هذا الشير وسوي شير جديد خلينا نقول.
نعم. جديد كمان. اوكي سا
ممتاز. هلا بس تضغط على الفيرست سلايد عشان نشوفها بشكل اكبر.
Yes.
نعم.
content.
اوكي.
اضغط على ديسبلاي مود. عندك ديسبلاي مود تحت سلايد عندك 100% جنبها ديسبلاي فول ديسبلاي سو بنشوفك يعني افضل. لانه حاليا بنشوف سلايدز كلهم بس حجم صغير ما بنقدر نقراهم.
هسه اوكي.
دكتور سلايد
نعم.
شو اذا حضرتك تختار السلايد شو حتى يطلع البرزنتيشن قدامنا هسه بس مجرد السلايدات بدها تطلع.
سلايد شو ولا انشو ولا انشو؟ من ده سلايد شو دو from beginning.
Start recording.
دكتور خلي يساعدوك يختاروا لك الشاشه كلها مو بس الباوربوينت حتى من تسوي سلايد شو تطلع لنا شاشتك تشير ويانا وتقدر تشوف البرزنتيشن.
Start recording.
Perfect. على بركة الله.
هسه اوكي.
ممتاز.
يلا. The particulate material is one of the major atmospheric pollutants. Particulate material in the atmosphere often contain high level of toxic metal and organic contaminant. Particulate material describe the wide variety of airborne material. PM pollution consists of material including dust, smoke, and soot that are directly emitted into air or result from the transformation of gaseous pollutants. Particles come from natural source, for example, volcanic eruption and human activity such as burning fossil fuel, incinerating waste, and smelting metals. Objective of this study. The main aim and objective of this study are to determine the concentration of heavy metal like iron, Mn, copper, Pb, zinc, Cd, nickel, and copper in dust in the Hook area or the Hook city during the period from 2017 and 2018. The study also of the morphology of this dust and microstructure and chemical composition of particle present in the dust sample in the Hook city by using reflected light microscope, atomic absorption spectrometer, AIS, scanning electron microscope, SEM, and energy dispersive X-ray, EDX, along with the statistical analysis of result obtained. The study area was conducted in the Hook, as I mentioned, and which is north of Iraq, and the seasonal average temperature for between 2017 and 2018 the average was 33 centigrade for summer, 21.6 for autumn, and 10 centigrade for winter. The area is characterized by semi-arid climate with dry, hot summer and cold winter. This is the map of the position which we collected the sample. We have D1, D2, D3, D4, and D5. Different area in the Hook. Methodology. Atmospheric dust sampling. The sampling was carried out during the period ranging from June 2017 up to February 2018 for 3 seasons, summer, autumn, and winter. A total of 15 atmospheric dust samples from 5 locations were processed and analyzed in the urban area, as in figure mentioned. The sampling site were selected based on the following criteria. They were not shaded by any obstacle, and where the dust collect using funnel container of neck nozzle were installed on the roof of building about 7 up to 8 meters above the ground. The funnel of the top squared area 50 times 50 centimeters square covered with mesh on top to form a rough area for trapping to avoid animal The sample were then sterilized plastic bag and transported to a laboratory. Those samples were dried by oven from 24 hour temperature 105 centigrade, and then their weight were recorded. Chemical analysis by using atomic absorption spectrometer, AIS. An accurate weighted of 0.5 gram of dust after dried it and sieved it through 0.5 millimeter mesh was placed in the test tube to digest it. In the test tube contained 10 ml of the ratio 3:1 concentrated of HCl and HNO3. The mixture were added to each test tube, and at room temperature the mixture was left overnight. Each test tube was covered with an air condenser and reflects gently at 80 centigrade for 2 hours. After cooling, the digested sample were filtered through moisture Wattman filter paper and diluted to 50 ml volume with the distillated water. The final solution were analyzed, characterized by heavy metal HVM such as iron, Mn, copper, P, Zn, cadmium, cobalt, and nickel using atomic absorption spectrometer. Scanning electron microscope and EDX microanalysis. Particle size and elemental composition of PM were obtained through scanning electron microscope and using also EDX. The spectra of particle were obtained after scanning an electron beam with an accelerated voltage of 10 kilovolt for determining of elemental chemical composition for the particle. The working distance was 4 millimeter, with the energy dispersive X-ray spectroscopy or EDX. The EDX micro or elemental analysis using line scan analysis technique and present element were both qualitative and quantitative measured for dust sample. Statistical analysis. Descriptive statistical include minimum and maximum, mean, median, standard deviation, and coefficient of variance curve were performed using SPSS package version 16. Light microscope and atomic absorption. The dust obtained has heterogeneous composition due to its varied origin, transport, and emission. The dust particle varied greatly with respect to size, morphology, and chemical composition. Particle trapped in 200 micrometer mesh were represented mainly by large biological material that was visible to the naked eye. Small insects such as wasp and other fragment of wood and were shown by the light microscope. Inorganic particle and synthetic fiber were also found. The Mn, Cu, Pb, Zn, Cd, nickel, and cobalt obtained by using AAS are given in table below. This is shown in for 3 seasons, in summer and autumn and winter. And then we found the concentration for each case. For example, in summer, it was Pb, it was greatest of them. The same thing in autumn, and then copper come in second, was greater than Fe. The zinc and cadmium detected only in sample SU1 and SU4 and not detected in other sample. Also nickel and cobalt not detected, which indicate that there is a very low concentration of these elements, so they cannot be detected. Variation of Fe, Mn, copper, and Pb concentration for 3 seasons for all locations are shown in the figure 2. This figure shows the concentration or variation of heavy metal at 3 seasons. Scanning electron microscope and EDX. Morphological feature of particle were observed. The size distribution analysis of particle is shown in figure 3. These particles were mostly of the large size and with a diameter ranging from 0.4 up to 7.5 micrometer. The average value of the diameter was 2.7 micrometer. Also, the particle display variable morphology. The shape vary from rectangular to irregular, from spherical to oval-like aggregate. This is shown the scanning electron microscope, and also we have this one for the EDX, for the element shown. Figure 5 and 6 below depicted the typical microphotography of aluminum silicated particle with the diameter less than 8 micrometer. Scanning electron microscope also shown large metallic particle found in the dust. So this figure 5 shown the particle at magnification of 50,000 and higher magnification 100,000 magnification. Based on the morphology and elemental composition study of the particle in dust of Indihok city, where we can sorted these particles into 3 categories. First, mineral particles derived from soil, sedimented and weathered rock surface, for example, silica particle and aluminio-silicated particle, clay or kyanite. Second, metallic particle derived from the industrial activity, for example, Fe, ion, and third one, it was the biogenetic particle, for example, pollen derived from plant which consider as potentially allergenic. Description statistical of heavy metal concentration in the Hook city are given in table 3. This table shows the statistical showing the minimum, maximum, and medium standard deviation and curve for the each case in the 3 seasons. The average concentration of heavy metal during 3 seasons are shown also in figure 7 below. The PB concentration is higher than other heavy metal, and the PB concentration is higher than other heavy metal. You see this figure 7, the average concentration of Fe, Mn, copper, and Pb in for 3 seasons. The copper concentration varied from 1.1 up to 27.1 ppm, with a higher mean value, and it can be released to the urban environment as a result of wear and corrosion of metallic part of the automobile. The Fe concentration ranged from 2.6 up to 24.6 ppm, with higher mean value 14.8 ppm observed in the summer season. Figure 7 shows that the concentration of all heavy metal in summer season is higher than other season. This higher concentration may be due to higher speed of wind and dryness of the soil due to low level of rainfall. Conclusion. This study demonstrated the potential of urban characterization of PM pollutant in district urban environment. The combination of AAS, SEM, and EDX technique together with the statistical analysis are valuable tool for the characterization of the particle of the dust at the Hook city. The identification of the morphology and chemical composition of the dust particle provided valuable information for the determination and tracing of their origin. The result obtained shows the presence of wide diversity of particles from natural, for example, crystal, of the air pollution in the Hook city are gases wasted in the form of vehicle exhaust emission from the diesel generator, agricultural fire, and electric power plants from Cache region producing electricity to the Hook area in the west side of the Hook, as well as dust input from south and west of Iraq, in addition to the rapid increase in building density and high population density. The analysis of heavy metal contamination such as Fe, copper, and Pb and Mn in dust of the Hook city is various from location and some season of 2017 up to 18 by using AAS along with the statistical analysis indicate that the heavy metal contamination increase according to the following trend. We see that Pb was greater than Fe and Fe greater than copper, then greater than Mn during summer season, and Pb greater than copper, greater than Fe and Mn during autumn season, and Pb greater than copper, greater than Fe and Mn during winter season. Among individual particles of tested dust by EDX were silicon, Fe, CaAl, Mg, Ti, and K. And the predominant element are silicon, was 16.7 weight percentage, Fe 10.6 weight percentage, Ca 10.6 weight percentage, and aluminum 5.9 weight percentage. Thank you very much.
Thank you very much, Dr. Kamil, for this very interesting presentation. Really, I mean, this topic is of high interest, including here in France. I mean, many cities are concerned about this kind of airborne contamination. So we will come back to you hopefully with questions at the end of the session. Thank you very much again.
Thank you very much. Thank you.
right now, we will pass to the following speaker, Dr. Qabila Faris Hamoud, from the Zaytuna University in Jordan. She's going to talk about environmentally friendly cities with reducing of energy consumption for residential building typologies to suit the climate environment. So, Dr. Qabila, are you with us? The floor is yours. If you could stop your sharing, Dr. Kamil, so Dr. Qabila can share her slide. Thank you. I don't know if she is with us or not. Just a second, Baba. Okay.
I think in the last minutes, Dr. Qabila withdrew her presentation. So we may jump to the next one, if.
There is no next one actually, no?
Okay, then we have the whole rest of the time for discussion. And
all right, okay. So I didn't see, because I got disconnected, I don't see any question in the Q&A. I don't know if the presentation were very clear or clear enough so that didn't generate any curiosity or question. But again, I will call everybody. We can even give the floor to open your mic and ask direct question to the speakers. So please go ahead. Anyone has a question? Please present yourself, your name and your institution, and then go ahead with the question.
I also cannot see any of the questions either in the chat or in the Q&A. So
yeah, there is no question actually.
yeah.
There was one at the beginning in the Q&A, but
maybe Dr. Suhad.
السلام عليكم دكتور جواد.
عليكم السلام ورحمة الله وبركاته. تفضل.
Could you, Sarwar, please, could you please explain the procedure for your work? Mr. Sarwar, could you please the procedure?
Dr. Sarwar, are you with us?
Yes.
Yeah, I am with you. Dr. Suhad, we had an experiment of columns. Components of the experiment are 3 types of soils having different salinity. We show you the ECs for all 3 types of soils, and we had an alternative irrigation for the adding water to these 3 columns, to these 3 soils with well water. One of them is the well water, and the other well water magnetized with a device of magnetization, and then
explain for the audience, maybe if there is a certain slide that can help you.
Sorry?
You may share your screen in case if you want to explain things on your slides. I mean, to make.
Okay.
Yes.
Okay.
I mean, just for the rest, also you can share your screen in case if you like to answer specific question.
Actually, I didn't display the detail material for the time you have. We had a little time for explaining the research, but I can explain it in detail for Dr. Suhad if you give me a time.
All right. Thank you very much, Dr. Sarwar. We have another question in the Q&A from our friend and colleague from the Global Academy, Vani Narita from Indonesia. She is asking, she is asking me about if the RO solar system water purification could work also during flood seasons when there is relatively no sunlight. Yes. So thank you very much for the question, Vani. Actually, yes, some of the limitation of the solar RO combination is if there is no obviously sunlight or during the night or during cloudy days obviously we cannot generate or produce the same amount of water, or you cannot produce water. So that's why actually we have this configuration using the battery, so we can store the energy, and whenever we don't have, you know, the sunlight, we can still have energy to run the system. Otherwise, also there is the hybrid configuration in which we have the system connected to the electrical grid. So whenever we don't have enough solar radiation to run to generate electric energy to run the system, the electrical grid, you know, do the job. So yes, those are some of the limitations of such solution, and we can only rely on this one of this kind of configuration. Either we have batteries, they are still expensive in the market, the prices are expected to decrease, hopefully, or hybrid system, so with a grid. So when you have electrical grid, so we can still rely on the electrical grid to cover those days or hours where when we don't have sunlight. I hope I respond to your question. Actually, in this regard, we launched last 2 years ago in my organization, the Middle East Desalination Research Center, where I have been working for the last 5 years, in an international challenge, which is called Oman Humanitarian Desalination Challenge. It's about $700,000 that we are offering to anyone in the world who can develop small desalination device that could be deployed in remote areas whenever we have a natural disaster or like tsunami or earthquake or floods. So people don't have water or don't have good water to drink. So we can intervene immediately with such individual devices to, you know, to make them survive. Such devices is, I mean, actually is a challenge, because we are talking about small devices that could produce at least 3 liters fresh water per day. It could be only $20 maximum per unit, etc., etc. A certain number of criteria. So we received actually a huge number of proposals in the first year. This year, also last year, I mean, we received also like 50 devices or proposals, and we are now in the phase of evaluation. My colleagues in the center are doing the evaluation right now, because I left them 2 months ago, and we are expecting to have, you know, solutions that, you know, because some of the solutions were very nice, but they didn't take into account this factor. For example, some of them are solar cells, are relying on solar radiation. So if you don't have sunlight, so it may not work. Our criteria was to produce 3 liters per day, every day, at least 1 month. So it shouldn't stop. So this is obviously very challenging. So that's why we need to find other solutions in which they take into consideration this factor or this weather conditions. Any more questions? I see no more questions. Actually, we had diversified the presentation. So we talked about desalination. We talked about grey water treatment. I don't know if Dr. Shaima is still with us. I don't know if you faced any, you are facing any issue with the acceptability. You know, this is not only for grey water treatment, obviously, it's for all the wastewater treatment in the Arab region. A lot of farmers and people, you know, they don't accept this, you know, whenever they know that these crops are irrigated by wastewater or used wastewater, you know, they are not encouraged to consume it. So did you face any issue, or did you do any work on this kind of aspect of acceptability? Dr. Shaima? I don't know if you, do you hear me? Does anyone hear me here?
Okay, I am with you, Dr. Gawat. سامعني حضرتك كويس؟
شكرا. Yeah, very good. Yeah, thank you.
Okay, I have questions, بس معلش ممكن يعني هيبقى فرانكو أراب عشان أقدر أعبر عنه كويس، لأن أنا مش في التخصص زي حضرتك. إحنا عارفين إن الووتر شورتج، فريش ووتر شورتج دي مش مشكلة فقط في المنطقة العربية، بل في العالم كله، والعالم كله بيتجه للديسالينيشن. فده أنا شايفة هيبقى فيه مشكلة مقبلة ما بين الدول كلها في العالم على إن استخدام المياه عشان أعملها ديسالينيشن. فهل في جايد لاينز بتعملها منظمات دوليه لتنظيم الموضوع ده. دي حاجه. الحاجه الثانيه، انت حضرتك اتكلمت كتير جدا عن environmental impact في الديسالينيشن، فانا شايفه ان في مخاطر كبيره جدا على المارين لايف، وده انا از مايكروبيولوجيست انا عارفه ان ده شيء يعني خطر جدا جدا، لان دلوقتي جزء من الاتزان البيئي احنا بنعتمده على المارين لايف. فشايفه ان استخدام السي ووتر والديسالينيشن هيأثر تأثير سلبي شديد جدا على المارين لايف. فانا كنت عايزه اعرف رأي حضرتك في الموضوع ده.
Okay, شكرا جزيلا. Thank you so much, Dr. Shaima. I will translate briefly the question because there are many participants who are not Arabic speaking. So, Dr. Shaima, concern was about the extensive or the intensive, use of desalination may be harmful for the marine ecosystem in the future, because we are witnessing a lot of projects everywhere, and this may be, will be a big challenge actually for the marine ecosystem. Yes, you are right. So when we talk about desalination, we talk about desalination of seawater, but also brackish water. Okay, I will start talking about brackish water. Brackish water, which are the salty groundwater. Because of in the last years, in many areas around the world, we have this seawater intrusion problem. The seawater intrusion problem is due to many reasons. Some of the reasons, for example, this problem is facing many coastal areas in the Arab region. So we have an increasing salinity of the groundwater. So the farmers actually in these areas, they don't have other alternatives. So to use this water, they need to use desalination, to reduce the salinity and make it valid or available for agriculture. From the other side, the seawater desalination also, because we have, as I said before in my presentation, we have almost 97% of the seawater covering the earth. So we have obviously a huge amount of seawater that we can use for desalination to produce fresh water for our needs. From the other side, environmental impact is a concern. So I think there are many approaches. One, we need to be strict in terms of legislation, which means that we need to impose to the desalination companies to dispose the brine after pre-treatment, and stick some standards to make the minimum impact on the discharge on the marine ecosystem. And the second point was, I already mentioned briefly in the presentation, that any desalination project obviously pass by the environmental impact assessment study, and this. Please, sorry, because I have the kids around, and this is the problem of the webinars. So I was saying that any environmental impact assessment study need to take into consideration the place, where is the best place to build our desal plant. We cannot just build it wherever we want. We need to build it in place where we study this marine ecosystem around, and we see where are the fish presence, the fish eggs, the different phytoplankton and the micro species that exist in the sea, and we try to avoid them. The other thing is that we are developing in many laboratories around the world many technologies to treat this brine. Some technologies rely on extracting the salts and minerals from this brine and commercialize it. This is one of the uses. The other use also is use the brine to cultivate microalgae for industrial purposes. For example, in some areas, they pump the brine in some ponds, and in this kind of ponds, they cultivate some kind of microalgae like spirulina. They harvest them, they compost them, and from them they extract fertilizers, and they can extract even some beauty products, etc. So this kind of applications are very interesting actually. So we can try to make more use of the brine and dispose less brine into the sea. The other way also is to innovate more and invest more in R&D to develop better technologies than RO. The problem of RO is the efficiency or the recovery. We get 70%, we are still producing a lot of brine. So we need to find alternative. Unfortunately, right now we have some very good technology at lab scale, but at the market scale, they are not yet there. So we need maybe a few years to get into better desalination technologies more environment-friendly technology. So I mean, desalination is there, is a solution, but we need to invest more and more to make it more sustainable. I hope I respond to the question because it maybe needs another conference. Thank you. Any more questions, comments? Mrs. Shireen, she is asking about the presentations. Yes, I can send it with pleasure. Maybe to the organizer, they can send it to everyone, or maybe I can put here my email address and you can contact me and I can send it to you.
Dr. Jawad, please, could I ask one question?
Please go ahead, please.
Dr. Jawad, were the results of the recycling RO highly efficient?
The process of recycling
the results of the recycling, yes.
You mean the recycling membranes?
Yes.
Yes, yes. Thank you very much, Dr. Shah, for the question. Actually, this is a very interesting topic because, as I said before, with the increasing number of desalination plants around the world, the concern is raising about the membrane because the membrane have a life cycle that could go up to 5, even to 8 years, depending on the conditions, on the feed water quality, etc. So the membrane, we need to find solution because for up to now, all the used membranes, or what we call end of life RO membrane, are thrown in the landfill. So this is a big problem for the environment. So what we proposed in our project 2 years ago is to recycle them. So the first way is to do some work on the membrane, for example, oxidation of the membrane. And so we get rid of the last layer of the membrane, and we can somehow convert this membrane to nanofiltration or microfiltration membrane, which could be still used in other processes. So we are right now, my colleagues are building now a pilot of wastewater treatment units based on those kind of membranes. If it is successful, we will look for upscaling this process and making it work at the level of big plants. I know some Spanish colleagues also and friends in Spain are doing similar work, like in MD in Madrid or the Sacir company. They are doing similar work on recycling RO membrane. So the process, there is no yet a guidelines to a clear process to do recycling of the RO membrane. But in the papers published already in this field, I can share with you some. They already explained the procedures, which kind of chemicals we are using, which kind of procedure we do in order to do the recycling. First, obviously, we start with the mechanical testing of the membrane. If there is no mechanical problem in the membrane, after that, we go to the chemical phase where we apply some chemicals to prepare those membrane to posterior use. I hope I could respond somehow, but I can share you with some papers that could be useful. Any more concern or questions? Yes. For Dr. Yeah, I wanted to ask, but Dr. Qabil is not with us today. So if there is no more question, then yes.
I may say something. If there's no more question and you end up with your discussion, then before wrapping up, I would ask the panelists to turn on their cameras so we can have a screenshot, like a memorizable one, for our. Yeah.
Thank you very much. I wanted to ask, but you did it. Thank you very much.
Yes.
So Dr. Kamil, Dr. Sarwar, if you could please turn on your camera.
Me.
Yes. Dr. Suhad.
Dr. Suhad, could you make it?
Probably Dr. Kamil left us, right?
Yes, I think too.
Okay, all right.
Okay, then let me take.
Done. Perfect. Thank you very much, everyone. Thank
Yes,
you to
thank
the
you.
organizers. Thank you to the speakers and all the audience for your attention.
Thank you.
Thank you very much. Have a good day. Assalamu alaikum.
Mr.